Good day, everyone. Today I'm going to lecture one topic in fluid mechanics and hydraulics on statical stability of floating bodies. So I hope that you will enjoy watching my videos, and I hope that you can understand and follow the discussions. So here we go. So I'll first discuss linear stability floating bodies. So consider a floating body like this, and this is the initial floating situation of this body here. And due to the downdraft force, external force such as wind or any other external force, naturally it will sink a little, causing an increase in the displaced volume, which increases also the buoyant force, which I call differential buoyant force, which acts upward. And so therefore initially or naturally the body will not be in equilibrium. So it will oscillate back and forth until such a time that the weight of the floating object and the buoyant force will balance again. And if it returns to its original position in the same fashion, floating fashion, then we say that the body is linearly floating in a stable manner. So we say in general that a floating body is said to be floating in a linearly stable condition when there is a restoring force or a force that tends to restore it to its equilibrium position. So exactly the same floating situation. But if it cannot float in the same position like this, so for instance, it now floats but in a different fashion, different manner, uh, it the topmost point is now on the left side or on the right side. Even if it floats, then we say that it is not linearly stable. Now, how about for rotational stability? So let's consider this composite body here. So let's have here a composite body where the bottom portion is made of metal and the upper part is made of very light material such as a foam. So let us say this is a very light material, but the very light material has greater volume compared to this metallic part, so that the composite body can float in this upright position. So the heavier metal should be at the lower part, but it is just enough for this metal to be fully submerged. So the upper part has greater volume and it is made of very light materials such as a foam or timber, but let's just imagine it is a foam. So due to the effect, so definitely the location of the center of gravity of the composite material should be closer to the bottom because the heavier part is at the bottom. And the center of buoyancy, which is the centroid of the submerged volume, would be above the center of gravity, such as that as shown. Due to the effect of wind or wave coming from, let's say, from the left, instantly the composite material will list to one side, it will tilt in the position shown, and let us study the result afterwards. So the weight acts at the center of gravity So a couple is developed which is clockwise due to that effect of the wind and wave coming from one side. And these are the locations of the weight and the buoyant force, and the sense of the weight and the buoyant force would be different or opposite to the couple that developed due to the effect of the wind and the wave. So, as a result, we expect that because of the restoring couple developed between the weight and the buoyant force, this composite body will go back to its original upright position. Because a restoring couple, due to the weight and buoyant force, tend to balance the couple that developed due to the wind and the wave. So we say therefore that a floating body is said to be in a rotationally stable condition when there is a couple that tends to return it to its equilibrium position, upright position like this. So for this case, if the couple developed between the weight and the buoyant force is such that it will counter the couple that developed due to the effect of the wind and wave combined, then there's a big possibility that this body after tilting will go back to its original upright position. So we say that the body is qualitatively in a rotationally stable condition. Then for the case where we have rotationally unstable situation, we use the same composite material, and by carefully placing it in a body of liquid or water such that initially it can float in this position with the heavier part on the upper part and the light part on the bottom portion. Let us investigate if it can go back to this original floating position. So still the center of gravity is located closer to the metal part, and the buoyant force is this time below because it is now the inverted position. So the effect of the wind causes it to tilt, and let us investigate what happens next. Again, a clockwise couple is developed due to the effect of this external force due to the wind and wave coming from one side, and the weight acts at the center of gravity and the buoyant force acts at the center of buoyancy. So the couple developed between the weight and the buoyant force has the same sense as the couple developed between the wind. So as a result, the couple that develops between the weight and the buoyant force will be in the same sense as the couple developed due to the wind and the wave. Therefore, it cannot go back to its original upright or original floating position. So we conclude that because it cannot go back to its original position because the couple developed between the weight and the buoyant force has the same sense as the couple developed due to the wind and the wave, then it is rotationally unstable. So in general, since the couple that develops has the same sense as the applied couple, this floating body is said to be in a rotationally unstable condition. So it is unstable. Then I now discuss the case where we have rotationally neutral stability. Such body would be that of this symmetric body such as spherical or cylindrical body, that the effect of the wind will just roll it, and there's no couple that develops because the couple will just be zero. It just rotates. So this body is floating in a rotationally neutral, stable manner because no couple is developed between the weight and the buoyant force. They are vertically aligned. So that's it for the qualitative discussion. So let's proceed to the measurement of stability of floating bodies. So we have measurement of the stability of floating bodies. So let us say this is the front view of a floating body such as ships or other floating bodies. So this is the initial water level and the ship floats in an upright position, initial position. This is called the axis of symmetry, the vertical line through the centroid or center of gravity, and this is the upright position of the floating body. The volume submerged or displaced is denoted by capital V, and the center of buoyancy would be located as shown. Center of gravity is, let us say, above the waterline section because ships, especially cargo ships, are loaded at the deck level also. So let's just imagine that the center of gravity in general is above the center of buoyancy. So due to the effect of wind and wave coming from one side, it tilts a list to one side in the manner shown so that the volume submerged at the right portion is greater than that at the left side. So we have a wedge, small wedge. We call this wedge of immersion, and it transfers there. And this is the wedge of immersion, this one. And this is the wedge of immersion. So because this is the axis of symmetry and the ship has symmetric frontal section, then they have the same volume except that this wedge is shifted to that right portion. So we will denote the volume of the wedge as small letter v. But the volume displaced is still the same because only a couple is applied. There's no additional load being added to the ship. So as a result, this original location of center of buoyancy will also shift to the right horizontally, and the center of gravity remains there. So from BO to BO prime. So the weight acts at the center of gravity and the buoyant force acts at the BO prime, the new position of the center of buoyancy. Now, take note that the principle is because of the effect of this wind and wave coming from one side, a clockwise couple is developed, and the couple developed between the weight and the buoyant force would be opposite to that developed due to the external couple. Then qualitatively we can say that this is stable, but that's not the quantitative way of measuring stability of floating bodies. So let's investigate further. So this line of action of the buoyant force, which is vertical, intersects the tilted or axis of symmetry that is now tilted also at the point of intersection called the metacenter M. And the angle between the axis of symmetry and this vertical line is denoted by theta, the angle of least theta. So that's the tilted position. This is the principle. The moment due to wedge shift, because there is shifting of the wedge, is equal to the moment due to shifting of BO to BO prime. So the moment of the buoyant force due to the shifting of the center of buoyancy from BO to BO prime. So the moment due to wedge shift is equal to the force equivalent to the weight of this wedge here displaced times the moment arm, or the distance between the centroids, and the moment due to the shifting of BO to BO prime is the moment of this buoyant force, which is buoyant force times MBO sine theta. From this horizontal distance here, we have a right triangle forming an angle of theta. So the moment arm is MBO sine theta. So let's consider this portion of the wedges. This is the wedge and this is the waterline section. And let's reveal the waterline section. Let's assume that this is the waterline section shown. Top view waterline section. And take note that theta is very small. So it seldom reaches 12 degrees, 15 degrees. Because if so, then if it is a passenger ship, the passengers uh, might be in chaos because of the very high tilting. So theta is imagined to be small. So let us say up to 10 degrees perhaps, or 12 degrees. In the worst situation, it will reach 15 degrees, but that is very small. That is small, considerably small. So this is the depth of this section. Take note that theta is very small. That's the height also of the differential area here. So this is the AW line on the waterline section. And the distance of the centroid of this strip from the axis of symmetry or point of symmetry is denoted by x. That's dA. And these are the locations of the weight equal to the weight of this wedge, or the buoyant force in the wedge. And the moment arm is denoted by S. So from this principle here, the moment due to wedge shift is F times S. And the moment due to the shifting of BO to BO prime due to the buoyant force is buoyant force times moment arm, which is MBO sine theta. So where F is specific weight of liquid water or seawater times the volume of the wedge, while BF is specific weight of the liquid times volume displaced, which is denoted by V. So if we cancel out gamma, then we have an expression for MBO, which is exact Vs small v times S, or V sine theta. Now the problem with this exact formula is for any angle theta, the volume of the wedge will vary. S will also vary, although the big volume is constant. And theta can be measurable. So this is exact but not practical formula. So we will develop an approximate formula. So also, by integration, the moment due to wedge shift is also the integral of differential f times x, or fs is integral of x times df times x, and replacing df by gamma times differential volume of the wedge, where this differential volume of the wedge is differential area, this top waterline section differential area, times the depth, which is this, the height or the depth of this portion. Now, because theta is very small, we can approximate this triangle into a circular sector with very small angle theta. And the arc length, this vertical depth, can be considered as an arc length, equal to radius, which is x times central angle theta. So replacing dv by differential area times height, and the height is this one, which is treated as an arc length of a sector with very small angle theta as mentioned earlier. Then from geometry, the length of the arc is radius x times central angle theta. So that's why the depth or arc length, the depth is x theta. So that's the differential volume. So replacing f by gamma or fs by gamma, then theta integral of x squared dA. Now the expression integral of x squared dA, take note that it is the square of this distance from the axis of symmetry, from this axis here of the waterline section, and dA. So this is the expression for the moment of inertia of this waterline section with respect to this axis of rolling or rolling axis. So Fs is gamma theta times I denoted the expression integral of x squared dA as I, moment of inertia. And that's the moment of inertia of this waterline section with respect to this axis here. So substituting into this formula here for Fs. So Fs, which is gamma theta I, is equal to gamma, this is also Fs, is equal to gamma volume MBO sine theta. We can cancel gamma again and derive an expression for MBO, which is equal to I theta over M over V sine theta. Again, this is an exact formula, but because in our assumption earlier that theta should be small, it seldom reaches 10 degrees, especially for very small angle of least, such as up to 5 degrees. And we can say from calculus that theta in radians and sine of theta will be approximately equal, that we can cancel them. So approximately for small angles, theta is equal to sine theta, approximately equal to tangent theta. You can try 3 degrees, convert that to radians, then press 3 times pi over 180 to 3 decimal places, compared it with sine of 3 degrees, compare it with tangent of 3 degrees, and you can verify that they are approximately equal. And this is only true for very small angles, such as those angles, allowed angle of least for cargo and passenger ships, to be practical. So for small angles, again, theta and sine theta are approximately equal, so that from this expression here we can cancel theta and sine theta, so that the expression for MBO becomes I over V. Although this is an approximate formula, but this is true for all shaped bodies. So for any body, floating bodies, this is true. But it is an approximate formula. It only becomes an exact formula when the body is floating in an upright position. So this is this formula I over V, I moment of inertia of the waterline section with respect to the axis, this axis here, rolling axis, we call this rolling axis, and V is the volume displaced. This is true, this is exact if the body is floating in an upright position. In the tilted position, this formula becomes an approximate formula. So that's it. So let's continue. Now, we observe that if M, the metacenter, lies above G, a restoring couple is developed. That is true in the previous slides. Therefore, the direct measure of stability of floating bodies is the term mg, called the metacentric height. So the distance between the metacenter and the center of gravity is the direct measure of stability of floating bodies. So if m lies above g, then it is stable and mg is positive. So therefore, the expression for mg is mbo plus minus gbo. We use plus if g lies below bo. Then we use minus if g lies above bo, just like the one I presented earlier. So when the center of gravity is near the bottom, below the center of buoyancy, mg will become very positive, and so it is very stable. So I consider the situation presented earlier that g lies above bo, so that there's a tendency that mg could be negative. So if mg is positive, then it is stable. If mg is negative, unstable rotationally, and if mg is 0, it is said to be in neutrally stable situation. So use plus if g lies below bo. If mg is positive, then it is stable floating. If mg is negative, unstable floating. And if mg is 0, it is neutral equilibrium. So let's go back to this situation here. So in a problem, there is a situation where the body is listing to one side or tilting to one side such that the edge coincides with the waterline section or the water surface, and it is called just on the point of submergence. So in an upright position, the term mg is called the initial metacentric height. And again, the metacentric height is the one that is being measured for the body to be called stable. So note that negative mg means that the body cannot float upright. For rectangular parallelepiped bodies, so let's develop an expression here using the same principle, and the dimensions are the width of the floating rectangular parallelepiped is b, the draft or the depth of submergence is d, the overall height is capital H, and the length perpendicular to the board is L. Now, BO is located, because this is rectangular parallelepiped vertical sides, at d over 2 from the bottom or d over 2 from the waterline section. And still, let's assume that G is above BO as shown. So that's d over 2. So that this is the waterline section, the length perpendicular to the screen is L. And due to the effect of the wind and wave, and it will tilt again to one side, and the wedges are triangular in shape, and the angle of this is theta. So we again separate it. So this is b over 2, b over 2. And if the angle is theta, then the height y. So that's the location of F, vertical, which is equal to the weight of the wedge. So that's also theta. We will resolve F into two components parallel to the inclined axis of symmetry, and the other one is parallel to the perpendicular to the inclined axis. So that this component is F cosine theta, and this component here is F sine theta. So that's F cosine theta, F sine theta, and for these components of F would be Same, f cosine theta and f sine theta. So the distance of the centroid of this triangular wedge from this axis of symmetry that is now tilted is x and x. So the moment arm is 2x, and this height of the wedge that is submerged here, which is equal to this, is denoted by y. So the centroid of the triangle is y over 3 from this line here, and this is also y over 3. So the total moment arm of f sine theta is 2/3 of y. In the same manner that the moment arm of f cosine theta is 2x, and x is 2/3 of b over 2. So times 2, that would be b over 3. 2/3 of b rather. So x is 2/3 of b over 2. So x is b over 3. Therefore 2x, the moment arm of f cosine theta, is 2/3 of b. While the moment arm of f sine theta is y over 3 plus y over 3, so 2/3 of y, and y is b over 2 tangent of theta. Tangent theta is y over b over 2, so y is b over 2 tangent theta. So the moment arm of f sine theta is 2/3 of y, and that is b tangent theta over 3. And take note that f cosine theta is clockwise, as well as f sine theta, the moment is clockwise. So let's now employ the principle that the moment due to wedge shift is equal to the moment due to the shifting of BO to BO prime due to the buoyant force. So that is f cosine theta times 2x plus f sine theta times 2/3 of y equals buoyant force times MBO sine theta. So replacing f, gamma's volume of wedge, and cosine theta, 2x is 2b over 3. So gamma small volume sine theta times 2/3 of y is b tangent theta over 3. Then equals gamma times big volume times MBO sine theta. Canceling out gamma and replacing small v by 1/2 b over 2 times y times L. Call that equation 1. So v is 1/2 of b over 2 times y times L. So v is b over 4 times y, which is b tangent theta over 2 times L. So on the next slide, v is b square over 8 tangent theta times L. B square tangent theta L over 8. So while capital V is BDL. So from equation 1, so let's recall equation 1 with gamma cancelled. So this is equation 1, gamma small v cosine theta 2/3 b plus gamma v sine theta b tangent theta over 3 equals gamma capital V MBO sine theta. So it becomes small v cosine theta times 2/3 of b plus quantity small v sine theta b tangent theta over 3 equals capital V MBO sine theta. So replacing small v and big V here, b square tangent theta L over 8 times cosine theta times 2/3 of b plus b square tangent theta L over 8 times sine theta times b tangent theta over 3 equals BDL times MBO sine theta. So let's simplify, cancel out BL and simplifying. So we have b square sine theta over 8, tangent theta times cosine theta is sine theta. Then over 12, because 2 over 24 is 1/12. And we cancelled BL. Then the second term becomes b square tangent theta over 24. B square tangent square theta sorry, sine theta over 24. There is still sine theta. Then we have d MBO sine theta. So canceling out sine theta and factoring out b squared over 12, then we have b squared over 12 times quantity 1 plus tangent square theta over 2 equals d MBO. Finally, we have an expression for MBO for rectangular parallelepiped bodies, only for rectangular floating objects. So MBO, this is exact. MBO equals b squared over 12d times quantity 1 plus tangent square theta over 2. Now, in an upright position, theta is 0. So this reduces to b squared over 12d. If you check the formula, exact formula earlier for all shaped bodies, I over v, and I told you that I over v becomes exact for all shaped bodies in an upright position, it reduces to b squared over 12d if you substitute. So MB equals b squared I over v, where moment of inertia with respect to the axis of rolling is LB cubed over 12, then volume is BDL. It reduces to b squared over 12d. Just like this when theta is 0. So we call that initial value of